So what we have today is mostly to accommodate for AC outages. So when we have utility power, we convert that through our power supplies to 12 volts. We give that to the load. When our AC goes away, we go to batteries, we turn on the generator, and then we feed the load with the same 12 volt. It doesn't realize that outage happened. Everyone's happy. What we have today looks like this. This is something that we kind of introduced at OCP about 2 years ago. We have 3 power supplies, 3 BBUs within a shelf. We have 2 of these shelves in every rack. There are 52 cells, 18650 cells in every BBU. These are power type cells. So think drills and screwdrivers. They have electric screwdrivers where they have high current density. We allow for 90 seconds of outage up to 3,600 watts. And the dimensions are listed here. The charging is pretty straightforward. Constant current, constant voltage gives us high reliability. There are 4 main limitations with what we have today. And we'll jump through these more in detail in the coming slides. First, we only have 90 seconds. So you can imagine you can't do much with a 90-second backup time. It's great for just transitioning to diesel backup, but other than that, you can't do anything else. The other one is we don't have any control over charge. So when you go through a discharge scenario, all the batteries want to be charged at the same time. That will become a problem for us, and I'll talk about that in a second. Lastly, the periodical charge mode that the batteries experience themselves, where it's driven by the self-consumption of the BBU, the cell, etc., is for us is happening too fast. Lithium ion doesn't like to be charged at its maximum voltage all the time, and it doesn't like to be at that state all the time, and it has adverse effect for us for degradation. Lastly, it's a challenge on thermals, where our data center is outside air cooled, and we maintain a certain range in the cold aisle versus hot aisle. We're seeing that over time our batteries are heating up. We'll talk about that in more details too. To talk about the discharge challenge, first I'll talk about a tool we have called Power Loss Siren. So Power Loss Siren is an application that runs local to the rack that lets all the hosts inside the rack know of an outage. That looks like this. So in a rack we have 2 zones, top zone and a bottom zone. We have 3 power supplies on top, 3 power supplies on the bottom, and they have their own associated BBUs. We have a top of rack switch on top of the rack. When an AC loss happens, the power supply detects the loss, sends a signal to the switch. Then the switch lets all the hosts inside the rack know that an outage has happened, and then the host starts backing up the data. That basically gives them time to, say, write all the user data into hard drive or offload it to a different rack. Today, with our 90 seconds, this being a typical discharge of our BBU, we release that signal at the 45th second. The reason it's at 45th second is because we don't want to keep triggering this backup signal. Our generator should turn on within 20 to 30 seconds, and we should write through any kind of outage. But if we're not up and running in 45, then we need to take action, and they have 45 seconds left to react. This is not enough. We're seeing that we can back up the majority of our data, but even a little bit of data lost on the user data is quite important for us. So we need to cover the entire thing. Let's talk about the charge challenge. So I'll walk through this graph. There are a couple of things happening. So you have the blue line, which is our main switchboard power. The green line is the actual load, and the orange line is the reserve switchboard power. So what's happening here is that at an outage event, you switch from your main switchboard to your reserve. This is a simulated experiment. And when you do that, you go through the batteries to fill in the transition of that switching. When you make that transition, the batteries have been discharged. Now they all want to be charged at the same time. So you get this huge peak on top of what you are already carrying on the load. This becomes a problem in 3 areas. One, you can trip the breakers at the DC. If you imagine if your data center is running at really high power, if you're trying to maximize your available power, now you have an additional buffer for charging the batteries. The other is if you actually have a generator as opposed to a reserve bus, then your generator could halt. Generator is just a diesel engine. It's going to have a certain limits for its turn on, a certain max limit for its turn on. You could halt the generator because of this extra charge power. Lastly, you can jump in, as we do, and we can cap the power. But capping power is capping the services, and that's not so nice to the services that are running. Let's talk about the thermal limitations. So we don't have any fans inside the BBU, and there's a whole list of reasons why we didn't add fans, but mainly around the fact that these are lithium-ion batteries, and we want to have the entire unit enclosed for safety. Our data center is outside air cooled. We have hot aisle and cold aisle. In the cold aisle, we maintain 18 to 35 C, and our hot aisle can go as hot as 45 or even more. It's really dependent on the time of year, whether it's summer, the time of day, how much load the data center is running, etc. What we're seeing is that over time, the batteries are getting heated up from everything around them. So hot aisle being hottest, and then you have servers running on the top or bottom, or even the power supply, and those are heating the cells inside our BBU unit. Lithium ion doesn't like to be in hot temperature. It accelerates its degradation. We need to do something about that from that perspective. So now I'll talk about what we're improving, the changes. So to address the discharge limitation, the time that we need, the extra time that we need, we're adding more cells. So the good news is the battery backup unit looks exactly the same from the outside. It's just longer. So there's going to be more cells added. And it's going to be an improved cell. The improvement in the cell is going to be towards the degradation of the cell at hotter temperature and elevated voltage. So this is going to be 84 cells, 14 series, 6 parallel configuration. So we've gone from 52 to 84. This can give us, at worst case power, 450 seconds of discharge. As well, we're changing the charge sequence where we want to have an adaptive charge, where it's no longer just a constant current, maximum power you can. Now it's adaptive from 1 amps to 5 amps. And we'll talk about how that's going to work out in a second. And the voltage is going to be increased, obviously, because we have increased the number of series configurations in the cell. What does that mean in terms of the time we get? Well, today we have 90 seconds. In our compute rack, we can have up to 600 seconds of discharge at worst case power. Or in our user database rack, which we care about and our power loss Siren really runs on, we can get up to 1,000 seconds of discharge. I have some discharge curves listed there as well in terms of the configurations with V2, where you have 3 BBUs running at the same time. Maybe you have a failure and running the worst case power. What it comes down to is that this BBU can supply up to 1,200 seconds of outage in a typical power loading for the rack when there's no failures in the rack. On the BMS side, we've simplified things as much as we can. We've added all the learnings that we had from V2, and we've tried to use simple ASIC for connection to the cells, for cell balancing, etc., and off-the-shelf components for the microcontrollers. One thing that we learned from the V2 battery backup was that when a failure happens, by the time we get to it, ship it back to the vendors, and they do a failure analysis, the batteries may have been drained in the months or a couple of weeks that are in transit, etc. And by the time they get it, they can't really figure out what's happening because the battery is already dead. So we want to add some sort of black box functionality to record the fault and record the events before and after when the fault happened, so we can always recover and figure out what happened to the failure. So let's talk about the variable charger. So how do we control 1 amps, 5 amps? How do we reduce that overhead of power that we want to associate to charging? So we know a cell comes in 0% to 100% state of charge. What we've defined is the areas where we are okay with letting the battery just go uncharged. So that's the green area. We're okay if you're within 100% to 80%. We can sustain any kind of backup, and we can sustain a majority of our applications. The red zone is where we don't want to be. That's where the cell is dead. The yellow zone is another area where we can play. Depending on an application, if it needs maybe 20 seconds of discharge, maybe we can let the cell go to the yellow zone and not charge it. That helps in turn the degradation of the cell as well. As well, to reduce that overhead of power that we'll be adding for charge, we're thinking that we would use the charger with respect to the energy that came out of the BBU at a discharge sequence. So we'll be counting the energy by the power supply or the battery backup unit, and then put back that amount of energy with attention to the minimizing of the power that's associated to the charge. If we have no power stranded at a data center and we can charge it at that time, we will introduce a charge delay. So we can say that now we have all this extra capacity. Let's leverage that for another outage event that may happen right after the first one. And let's not charge the battery. Or we can come up with a scheme to stagger the charge sequence across the data hall throughout all the units that we have in the data center. On the thermal side, it's pretty simple. Adding fans help. The catch here is that we're going to be adding fans and we're going to be running at an extra slow speed. It's only about 4 CFMs, and the simulation here shows how fast only 4 CFM can cool down the batteries after a discharge scenario versus not having a fan and just having the batteries cool down by themselves. So let's talk about the system improvements and limitations we have. So the hope is to use the batteries to have reduced generator uptime. That helps the emissions that as a result of running the generators. As well, it will help the cost that you need to associate to running a generator because you need to basically put fuel in there. You can do graceful shutdown in disaster recovery scenarios. So when a whole region goes down, you may have 15, 20 minutes worth of backup, and maybe you can do graceful shutdown. Maybe you can save your states. Maybe you can transition some of your traffic from one data center to the other. One of the goals that we're trying to set is peak power shaving. If we hook up our battery backup unit to the rack directly, then there's no reason why we can't run the power supplies and the battery backup units at the same time. So in an event of a max power at the data center, you could use the power from the batteries to give you a little bit of more boost on the max power available at every rack. The reason we can't do that, today is because everything happens through our power supply. So in a V2 deployment, you have the AC rectified to DC, and it sits on our bulk capacitance, which is kind of like our storage tank. And then we take the energy from that storage tank out to the load in 12 volts. The energy from the battery is put in the same bulk capacitance. Those guys can't be running at the same time because we're maximizing the power through that secondary part of the power supply. So our solution is to decouple that. So we'll have our power supply doing the rectification and stepping down the voltage and providing the power to the load. In parallel to that, we'll have the batteries either stepping down the voltage depending on what the load needs, or stepping up the voltage depending on what the load needs, and going directly to the load as well. Then for charging, we could either use the AC power to charge, or we can actually connect to the same bus and charge the batteries during non-peak times. That would look something like this, where we would take the batteries, just flip them on their side, and it would take about 4 U's worth of room in the rack. We could, when we actually flip them on the side, we could put as much as 8 units in an open rack. And then we can have controllers inside that shelf where we could use OpenBMC controller, which would be of great help to us because we're actually using that OpenBMC in other parts in the rack as well. In a rack, it would look like this, where it could sit somewhere in the rack, the shelf can sit somewhere in the rack, and in the case of a GPU rack for us, for example, it can give us more than 20 minutes worth of discharge. Why is that helpful for GPU racks? Is that these GPU racks are running AI training algorithms. If an outage happens, you could potentially put a checkpoint or save your training algorithm at some point before you turn off the rack, so you don't have to start that algorithm from scratch again when the AC comes back. The good thing is, since the BBU looks exactly the same as the V2, we could potentially reuse the units in the new shelf. Because again, it's the same form factor, it's just a bit longer, and it's sitting on its side. So I want to bring attention to this slide where we're actually spending quite a lot of time in this closed loop model where we typically go from design to manufacturing, and then we ship it to the data center, and then we use it. And then the data center goes through a hardware refresh cycle, and we get rid of that hardware. What we're trying to do with the batteries is evaluate whether we can reuse them. So we have a pilot program right now running in the data center where we take the batteries out and we evaluate whether they have enough capacity, and we actually put it back into the racks that are coming in, the new racks. Or we're trying to see if we can use it in an alternate application inside our data center or for an alternate application somewhere else. We're trying to close this loop through recycling as well. So lead acid has all this technology around its recycling, and a lot of raw material can be extracted from a lead acid battery. But lithium-ion technology is still not there. So we're trying to reach to our partners, reach to our recycling partners as well, to figure out what everybody's doing with these cells. How do they actually recycle it? Is it just changing hands, or is it actually being recycled to raw materials? Our call to action is pretty simple. We're going to be releasing the spec around Q3 2019, just like we did with V2. If you think this is interesting, and if you have any feedback for us on this, it'd be great if you can share that with us. Thank you. Any questions? Yes.
Hi, thank you for the good explanation. One question interesting about new design. If you're coming back to the slide where your rack located, couple of slides coming back, please. Yeah, your new BBU unit located in the middle. Right now, in current concept, just two separate bus bar available and not connected between each other. How you have a plan to connect one BBU to two separate power zones?
That's a great point. So there's two versions of this. So the existing rack, you're absolutely right, there are two zones, and they're separate zones. The other version of this, that's not illustrated here, would have two bus bars. And it's very simple to take one bus bar from the left, connect it to the top, or the one to the bottom. But as Steve will talk about the next generation of the rack, et cetera, then you may get a clue as to whether we're going to be sticking with two zones or one zone. Either way, it's flexible with the design.
Because current power supply from the suppliers who is manufacturing that for Facebook not allowed to connect two power shells between each other. Current sharing available just only between power supply, not between power shelf. Yeah, this my questions was.
Yep. So the configuration where there are two bus bars coming out of this shelf, you will have a 4+4 configuration where 4 of these units, battery backup units, will go, say, to the top zone, and 4 will go to the bottom. So you're still not sharing the power zones, but you're sharing the power supply with the battery. And then obviously you have to resolve your current sharing between the power supply and the battery.
How do you measure the state of charge and state of health?
Ooh, that's a really good question. The question.
Should I ask the question? Yeah, I was asking what's the state of charge and the state of health of these batteries. Will you be using Kalman filter or any other approach?
Yep, so that answer is a little bit involved. Yes, that's one of the approaches to be using a filter like that. State of charge, we'll be using basically simulations based on the chemistry of the cell. So we can talk about that more offline. The state of health is measured on a periodical algorithm that we have inside the battery, where every 90 days the battery wakes up, and regardless of what the input power to the rack is, it requests a discharge. So we have a simulated discharge scenario running every 90 days in the rack to discharge the battery to a certain point. And then from that discharge, we can determine the discharge and the OCV of the batteries. We can determine what the degradation of the cell was compared to the last time we did this sequence.
Okay. Any other questions?
There's one back there.
Yeah, I want to know the V2 generation, the battery basically is to be charged by the PSU, right?
Yes.
And but your new generation, the battery and the PSU, you say you can do the parallel, the discharge in parallel to upgrade the maximum, the discharge current. So does that mean, you drive the current, from the bus, 12-volt bus, then charge to the battery? So the battery is not controlled by the PSU anymore.
Yes. So the charge could come from the bus bar inside the rack, and that enables you to charge the batteries during off-peak times. So when the rack is not running maximum power, then you can charge the batteries, which is fine because you're not bothering the load. Or we can have the battery pack connected to the AC plug, and you could charge the batteries through the AC plug as well, through a converter.
From the AC power?
Yes. Well, you have to convert, you connect to the AC power, you convert that, and then you, in the shell.
Okay.
And then you charge the batteries.
Thank you.
Any other questions?